So welcome back. I need to find my pen. I got my pen. Okay, so let's start that track. We're going to look at forces to begin with. And so if you look in the textbook, it has negative signs flying around and stuff like that. And I tend not to worry about that. It's not that I don't care about the sign. I do care about the sign, but I don't think that's the best way to get the sign. So I'm envisaging two charges. You don't have to have a big charge and a little charge, but we need to define them, so we'll just have charge A and charge B. And in this case, charge A is positive and charge B is negative. So the force between them is attractive. So I'm showing here the force that B exerts on A. And just that language tends to be confusing. If you're getting the signs backwards, it might be because you're misinterpreting what the instructions are. This is the force that B exerts on A. We have the two charges separated by a certain distance. And you may recall from Physics 1, we said that Fg is equal to big G, big M, little m over r squared. And the thing about that was there was no repulsive forces because it's gravitational stuff. There's no repulsive stuff, so I didn't need to worry so much. But now I have to worry a bit because I have positive and negative charges, whereas I only ever had positive masses before. I'll have attractive and repulsive signs on the charges. But it's basically the same equation. It's just, you know, rather than big M, we have big Q. Rather than little m, we have little q. I prefer, over time, to have those two. I think it's much more illustrative of what's going on, but, you know, it's not tradition. I have absolute value parentheses around these things because I don't care about the sign. If you use the signs, you may end up with a positive force or a negative force. And that does not indicate direction. That indicates whether it's attractive or repulsive. And if you have a negative sign, it's an attractive force. And I don't know what you feel about that, but this is like, hold on, I thought we had a number line and I thought we had some idea about some logic here, and now these signs are making no sense. And my sense is, yeah, throw them away, though. The force is going to be a certain magnitude, so that's a positive bit. It will have a certain direction in space. So let's not deal with this. Let's deal with this in terms of magnitudes and unit vectors, and it'll work out nicely. The book tries to formulate that, so it says, well, for F1, 2 equals, and then it has the charges in a very specific order, and R1, 2 in a very specific order, and then you have a negative sign comes out of the blue from somewhere. And I just feel like, let's just look at the diagram. Just draw a diagram of the thing and look at it. It's obvious which way the force goes. So that's my plea to you is, you know, do that. What Coulomb's constant, 9 times 10 to the 9 newtons meters squared, Coulomb squared over Coulomb squared. Coulomb's constant is incredibly big. Only a few charges cause a huge effect. If all the atoms on this table were charged, I'd be spread out like an oil slick on this table. It would be pulling me so strongly. They're all there in mass, and I don't even feel them as I walk by. I can't close my eyes and say there's a wall over here and there's a wall over there because of proximity. You can't do that. In principle, you can. But I can't do that because it's such a weak force. The gravitational things are so weak. So this is a big number. Q is measured in coulombs, and R is the distance between the two charges measured in meters. Bit of point. Any electrical engineers here? In electrical engineering, they tend not to talk about Coulomb's constant so much. They talk about 4 pi over epsilon naught, which is in a way more fundamental. Okay? So you might see equations where it says F is equal to big Q, little q over 4 pi epsilon naught r squared. So it kind of looks like it's a different equation. But actually it's the same equation because 1 over 4 pi epsilon naught is just Ke. So you've got to watch out for that a little bit. If you're going along EE, they might just write things down a little bit differently. I remember nearly throwing a textbook away because it had the 4 pi epsilon naught stuff in there. I'm going, this is crazy, and just like, and then, oh no, it's just, you know. So, and the epsilon naught, which we'll get to, we'll use both of them, but epsilon naught is called the permittivity of free space. If I want it in vectors, well, I have the same old magnitude. That's my same old magnitude from the previous page. I'm just going to multiply it by a unit vector that's in the right direction. So I look at my diagram and I say, well, there's the force that I want. If I take my magnitude and I simply multiply it by a unit vector that's in that same direction, then I have my vector. So I don't try and change the magnitude. I just try and make a unit vector which has the right direction for the force that I want. So I get good at doing the magnitudes, and then if I want my direction, I use a unit vector for my direction. So to write it down clearly, this is our unit vector symbol, and this is my distance symbol, etc., etc., etc. Let's do one. What is the magnitude of the force experienced by a 3 coulomb positive charge? So let's go 3 positive. Located 4 meters from a 12 coulomb positive charge. I just want the magnitude. Well, they're going to be repulsive. So let's do a little bit of background thinking. Those forces are going to be equal and opposite because action-reaction pair. I say, whichever one of them I like. It says, what is the magnitude of the force experienced by the 3 coulomb positive? So I'm actually asking about that guy. But the magnitude of this guy is the same as the magnitude of the other guy. They're both the same magnitude, just opposite directions. So I say, well, Fe is equal to Ke big Q, little q over r squared. And this equals Ke big Q. Big Q is plus 12. I don't need to really worry about the signs, do I? Because I'm going to use absolute values. I forgot to write that in because I always use them. And on this one, it's going to be plus 3 over 4 squared, which equals 36 over 16 Ke. Don't forget my Ke. So Fe is going to equal, what is that going to be? 16 over 8? Is that right? No, 16, 36 over 16, 16, no, no, 18 over 16, which is 2.25 Ke. What have I forgot? Why is that answer going to give me sadness? Doesn't have units. Doesn't have units. That's what I'm after. It's got to have units, newtons. So what I notice is people start forgetting to put units in when they start leaving these letters behind. So just because you're... So in a test, I don't want you to put Ke in. Life's too short. There's too many questions. In homework, I'll often ask you to work out the answer to a numerical value for a couple of reasons. One is I want you to get a feel for the size of things, and Ke hides a whole bunch. It's hiding 9 times 10 to the 9. It's like, you know, a whole bunch of force it's hiding. But for a test, I don't mind leaving it in. But the downside is when people leave it in, they tend to forget the units. So watch out for that. What is the magnitude of the other one? If we call this Fe3, Fe12, I just made that up. Fe12 is going to be equal to, what would the magnitude of the force on the 12 positive be? 2.25 Ke newtons. It's just the same because it's an action-reaction pair. Cool. Cool. Oh, ijk vectors, 3 Coulomb point charges located at that position, 12 Coulomb point charges located at that position. What is the vector force experienced by the 3 Coulomb charge? You could draw me a nice 3-dimensional IJK diagram and point those two guys on there. And it would make your diagram a bit complicated. You don't really have to draw it to scale. You've got to get the kind of principle behind it. And so I'm going to draw a diagram. There's my origin. I'm going to do that guy there. And there's my 3 positive. And this guy is 2I plus 3J plus 4K meters. And so that is a position vector or a displacement vector from the origin. Okay. And if I think about this other guy, now I'm not trying to draw this in the least bit to scale. I'm just putting in 2 different positions. And this would be 3I plus 5J plus 1K meters. I'm going to change colour pens so you know I'm doing something. Now I'm thinking about that. Before I was writing down information, and now I'm going to think about that. And of course what I'm going to realise is I have a force in that direction, and I have a force in that direction. But I'm not interested in both those forces. I'm only interested in one of them, and it is, what is the vector force experienced by the 3 Coulomb point charge? That's the force that I want. So I say, well, F for the 3, Fe for the 3 is equal to Ke, big charge, little charge, over R squared. There's my magnitude, multiplied by this unit vector. Put an arrow on top of this so I know I'm talking about a vector. And I can begin. I can say, well, Fe for the 3 is equal to Ke, and that's going to be 12. That's going to be 3. And now I'm in a bit of a pickle here, because I don't know what the R is. I know what it is on my diagram. It's the distance from there to there. But I don't know what it is. Okay? So I'm going to change colour pens because I'm doing a little bit different thinking now. Yeah.
I was wondering if this would work. Would we be able to find, just do the distance between those 2 vectors?
Oh yeah, that's what we're going to do. Yeah. So you're ahead of me. Good. So I got to pick a direction, and the direction is going to be either from 3 to 12 or from 12 to 3. It doesn't matter as long as I'm aware of what I'm doing. And I'm going to pick, a bit perversely, I'm going to pick that direction. I'm going to pick, in a way, the worst direction that I could pick. I'm going to call this one R1. I'm going to call this one R2. I'm going to call this one R3. And I want you to think about your vector diagrams that you did in Physics 1. And I'm going to give you 3 possible equations. R1 is equal to R2 plus R3. R2 is equal to R1 plus R3, or R3 is equal to R1 plus R2. Only one of those is right. And I want you to look at the diagram and try to decide which one of those is right and why. You've got a diagram, it's got vectors on it. There's 3 vectors, 2 in red, one in black. And they're related to each other. They're a vector diagram. They're related to each other. So is it that R1 is equal to R2 plus R3, or R1 is equal to, or R2 is equal to R1 plus R3, or is it that R3 is equal to R1 plus R2? And I'm going to tell you the right answer. I'm going to see if you can then justify it for me. So commit to something, though. Commit. Don't wait for me. Commit. And I'm going to tell you that the correct answer is that R2 is equal to R1 plus R3. There's the correct answer. Now, if you got that answer, what was your logic? Anybody get that answer? What was their logic? Yes. What was your logic?
Because when you go for R1, you're going from the origin to that point, and then because R3 is going downward, the R1 and R3 to get you to where R2 would be.
So what you're recognizing is the process of vector addition in a diagram. And the process of vector addition in a diagram is you put the tail of the second on top of the head of the first. So you said, oh, it must be R1 plus R3. That's what you're adding together. That drawing means you're adding these two guys together. And that's the resultant. So these two equal that resultant. So R2 equals. Well done. That's exactly right. Okay. So now I'm going to do a little bit of erasing. Let's get rid of that erroneous one. Let's get rid of that erroneous one. And then I'm going to do, this is going to be a bit long, but okay, don't care. Pen. So we're saying R3 is equal to, sorry, R2 is equal to R1 plus R3. Then come along here and then go, so that means that R3 is equal to R2 minus R1. Agreed? Now I'm using, arithmetic. I'm saying, okay, I want R3. Let's move that to the other side. Agreed? So I go IJK. And I write down R2. And R2, looking at this diagram, is 3, 5, 1. And I want to have minus R1. Minus R1 is minus 2, minus 3, minus 4. And that says to, which equals R2 added to minus R1. So that says to add. So I go plus 1I plus 2J minus 3K. And that is R3. Agreed? So I just dropped in there a little bit of vectors that we'd done before. We did it in Physics 1, but we've not done it for a while. So that's just a bit by the side, yeah? Agreed? Everybody okay with that? I could have been nice and just told you that the displacement vector between the plus 3 and the plus 12 was 1I plus 2J minus 3K. I could have just given you that black vector, but instead I decided I was going to make you work for it. So, okay. Now, given that information, I need to know the size, the magnitude of this R3. I need to know that size. And how do I find, given the vector, I know the vector, given the vector, how do I convert the vector into a magnitude? Yeah, I use Pythagoras in 3 dimensions. So I'm going to go 1 squared plus 2 squared plus, it's minus 3 squared, but I'm squaring it so it's the same as plus 3 squared. That's my magnitude. Oh, I forgot one thing. Most common mistake. Forgot to square it. Because it is r squared. Can you see how if you write down the equation, there's a good idea that your eye will catch it. If you don't write down that equation, you're done. I just lost points. If I hadn't written down that initial equation and didn't square it, man, I don't know the equation. It's like, I'm halfway there. I need to have a unit vector going in the right direction. The right direction is that. I need to have that guy. I know it's on the same line as R3, but it's in the wrong direction. So how can I take that into account? If this is R3, that's plus 1i plus 2j minus 3k. That's on the right line, but it's pointing in the wrong direction. How can I make that point in the right direction? Change the signs. I could change the signs by making that a negative and that a negative and that a positive. Or what the book sometimes does is it puts a negative sign in front, which is kind of, it's the easy way of doing it. But man, it's confusing the first time you see that. Why was that magnitude a negative? It's not a negative magnitude. I'm just changing the sign of my vector. Now it's in the right direction, but it's way too long. And how can I make it have a unit vector? What do I do to make a vector into a unit vector? Divide it by its own magnitude, which is 1 squared plus 2 squared plus 3 squared. I'm gonna do something now. That's your answer. If I say, and I will, write me an expression for the force experienced by. That's what I'm looking for. If it's going to drive you crazy and you say, well, hold on, that's completely unraveled. I'm going to go minus 36 ke over 1 plus 4 is 5 plus 9 is 14. If you prefer that, I can do that as well. But I don't want you to multiply it on and give me a decimal with I and a decimal with j and a decimal with k. Because for me, grading, I can literally look at this and I can say, oh yeah, God, they've got the big Q and the little q, and yes, they've divided it by its the magnitude of the vector squared, and then they put the negative sign in so they could change the direction of that vector, and then they normalize that. I know you got the right, I know you know how to do it. So for the test, I want you, when I say using write an expression for, I mean either of those two. That's what I'm after. And if you can do that, you got the skill, and it's going to come up. I can tell you that's going to be on test 2. Or it might be electric field as opposed to electric force, but it's the same. We'll see in a minute. It's the same thing. Okay? And I think the trick is, because you look at the book, and that book's going to have a negative sign there, and it's going to have F, 1, 2, and then 2, 1 in there, and it's going to be very stylized. And when students learned it that way, half the class would get it right, and half the class would get it wrong. And I'm very keen you get the right sign on it. I'm very keen on that. So there will be points for that, correcting that sign, for getting the right direction for the vector. And that's the last thing that clicks in. People, when they first begin, they don't get much of it, and then with a bit of practice, they get better and better at it. And the more subtle bit at the end is, do they get the right sign on it? And that's what I want you to be able to do that. It's coming up, so get ready for it, yeah.
So when we were deciding our R3 vector, would it have been easier to just have the R3 to point in the
And that's exactly right, and that's what in real life I would have done. But then I wouldn't have had that conversation with you. So I was in a way choosing the worst case, so that, you know, given that worst case, okay, so I need to accommodate that time. But yeah, that's exactly right. My advice is always pick the direction of your vector in the direction of your unit vector, and then you don't have to worry about that sign. It'll carry itself forward. Okay? So it's a nice skill. And you could be doing this with electric fields, and we'll do it later with, we're going to do vectors a lot. Point charge is located at some distance from a y. So here's x and here's y. The charge x experiences a force of 18 newtons towards y. So this is 18 newtons. And then this is just basically conceptual stuff based on that. What can you conclude about the sign of the two charges? Anybody? Got to be different, don't they? Because it's an attractive force. If they're the same, they're going to be repulsive forces. So they're going to be different. And then what's the size of the force experienced by charge y? It's also going to be 18 newtons, isn't it? And then what direction, well I just did it actually, what direction will the charge on point y be? It's going to be towards x, isn't it? Yeah, because it's an attractive force. And what can you say about the magnitude of the two charges? D.
Yes.
What's your justification for D?
You don't know how far away they are?
No, the same distance, you know. Can you give me an analogy from mechanics that convinces you that it's D? Isn't this a bit like the force between a truck and a love bug? Force on the love bug is the same as the force of the love bug on the truck is the same as the force of the truck on a love bug because they're an action-reaction pair. Yeah. So it's tempting to say they're the same because of the same force, but in reality, they need not be the same. I pull the sun with the same force that the sun pulls me because we're a reaction-reaction pair. So you can't say anything about the size of the two charges. It could be 1 billion coulombs to 1/1000th of a coulomb, and the forces will be the same. So that's taking us right back to good old Newtonian thinking. And it's Aristotle thinking is so ingrained, that's going to be a question that catch out. I think in discussing that with class last time, I think I got that wrong. I think I just walked right through it. You got to keep coming up. We got 7 minutes, just by the way. Okay. A point charge is located some distance from point Y. Charge experiences 18 newtons. What force would charge experience if the separation between two charges were tripled? Sorry, that's X. And that's Y. And that was 18. And now we're going to triple the separation. So this is going to be, well, Fe is equal to KEQ, Q over R squared. If I double my separation, what happens to my force? If I double my separation? It's a quarter because it's an inverse square, isn't it? If I triple my separation, it's 1/9, isn't it? So it's going to be, 18 over 9, which is 2 newtons. Yeah? Because I separated them by 1. I did that intuitively, didn't I, in my head? Can't do this next bit intuitively, it's too complicated. Got to do this more formulaically. The trick with these is you think about the basic equation and then you say my new force over my old force and then you put your old force in, and the old force was 18, is equal to, and then you say, well, that's my new Coulomb's constant, my new big Q, my new little q, over my new separation squared over my old Ke, my old big force, my old big charge, my old little charge over my old separation squared. And then I'm saying, well, I didn't change Ke, so let's just call that 1 and 1. My charge, what force would Y experience if the separation between the charges were triple? Let's do it in order. So if the separation is tripled, that was a 1 squared, and now it's a 3 squared. So that's the separation tripled. And the magnitude of x was doubled. So this was a 1, and now it's a 2. And the magnitude of the y is quadrupled. So this was a 1, and now it's a 4. And of course we're cancelling all those out. So that's going to be 8 over 9, yeah? And it's amazing how many people will put down that as the answer. But if you think about it, it was Fe nu over 18, which equals 8 over 9. So Fe nu is going to be 16 newtons. 2 8s are 16 newtons. So back to our old ratio problems, yeah? Cool. Let me just click one more thing. Cool. Back to our old ratio problems. Question? Yeah, comment? Okay, cool. Next time we have a quiz, okay? I made quiz 3, I just moved quiz 3 back, so this is online, so you can just look at it. What do I want you to know for next time? We've done prefixes. And we did prefixes with the geometry. Remember the geometry was the spheres and the triangles and the, etc. I can guarantee you that I will also have the force equation on there. So one of your questions will be Fe is equal to Ke big Q little q over r squared. Either magnitude or vector form, so R with a hat on it if it's vector form. That equation I want you to know for next time. Okay? Yes. Just write it down. I'm going to turn around and say, what is Coulomb's equation in vectorial form? So you'll know it by name. Okay, that's the equation. That will be on there. It's like I'm not going to tell you to learn it and then it's not going to be on there. That will be on there. So review your prefixes, review your geometries. Oh, and the other thing is, we'll leave the, well, no, I want to do it before the test. So if I asked you to do 36 divided by 2 pi on a calculator, I want you to know that it's 3/6 divided by parenthesis 2 pi parenthesis, or 3/6 divided by 2 enter divided by pi enter, not divided by 2 pi. Can you see how you get the wrong answer if you do divided by 2 pi? So I'm going to try and think of a way. I might not be able to do it for this next time, but that's coming up. I want to get a way that I can just drive in the fact that you got to use parentheses or you got to be more careful. Yeah.
Are you going to upload quiz notes?
On this one, no, that was probably it today. so.
Pretty much just the last 2 quizzes and that right there.
Yeah, exactly. Yeah. Know this new equation. Last 2 quizzes. We got lab? Are we in lab next?
Yeah.
Okay.
No. You called it off. You remember that?
I guess that's a firing offence.